You can review content from Crash Course Organic Chemistry with the Crash Course app, available now for Android and iOS devices.
Hi, I'm Deboki Chakravarti, and welcome to Crash Course Organic Chemistry, and to my home, where we are filming now because of the pandemic. When your fancy clothes say dry clean only, maybe you just never wash them. When I was little, I thought dry cleaners dusted laundry detergent on clothes and then just ran them through a machine to get rid of the powder. Dry cleaning isn't actually dry though. It's just using a liquid other than water to wash dirt away. The most common liquid is tetrachloroethylene, also called perchloroethylene, or PERC for short. But dry cleaning, like everything, comes with accidents. And unlike a water spillage, a PERC spillage can be harmful to the environment. We don't have a great way to clean up PERC chemical spillages right now, so we may need to get creative. Industrial plants use some species of soil bacteria to clean up waste products like 1,2-dichloroethane. These bacteria have an enzyme that removes the halogens through SN2 reactions, replacing them with more palatable alcohols. So the waste chemicals can be eaten by bacteria, processed, and even reused in things like plastic manufacturing. PERC's double bond makes it unable to do an SN2 reaction, so it's a challenging compound for bioremediation, but maybe someday chemists and hungry bacteria could help with this pollution. For now, let's dive deeper into SN1 and SN2 reactions to find out how substrate structure and other reaction conditions can help us pick a likely mechanism. In episode 20, we learned about SN1 and SN2 pathways for substitution reactions. Being able to figure out which one takes place will let us predict the correct reaction products. Remember, SN1 has a carbocation intermediate and results in a mixture of stereoisomers if a chiral center is reacting. The SN2 mechanism is a concerted process and gives inverted stereochemistry at a reacting chiral center. There are three key players in our substitution reaction dance, or merry-go-round, or whatever visual you like. An sp3 hybridized carbon substrate, a leaving group that can accept electrons as it departs from the molecule, and a nucleophile, something with a lone pair or pi bond. Recognizing good leaving groups can help us determine if a substitution reaction can take place. For example, weak bases with strong conjugate acids are good leaving groups. Weak bases are happy to float around by themselves in solution as anions. Most halides fall into this category because the pKa's for HCl, HI, and HBr are big negative numbers. Other good leaving groups are sulfonates, compounds that come from acids with negative pKa values. They're big molecules, their electrons are spread out and stabilized by multiple resonance structures, and they have special non-IUPAC names like tosylate, mesylate, and triflate. If the group we want to leave doesn't want to let go of the carbon chain, substitution does not happen. We call these poor leaving groups. Poor leaving groups tend to be strong bases, which are less stable than weak bases out on their own in solution. Examples of poor leaving groups include hydroxide, NH2-, CH3-, and hydride, all with weak conjugate acids that have pKa's above 12. However, sometimes we can turn a poor leaving group into a good one and entice it to leave by protonating it, sort of like offering your friend candy to give you their spot on the SN1 merry-go-round. So, like I just said, hydroxide is a poor leaving group. But if we add a proton to it, the leaving group changes to water, which is happy to swim away in solution, leave behind a carbocation, and get substituted by a nucleophilic bromide. We need a good leaving group for both SN1 and SN2 to happen. But in organic chemistry, we'll often be asked to choose which mechanism is more likely for a given substitution reaction. So let's look at three key factors that can help us decide whether to do SN1 or SN2. The first and most important factor is the structure of the substrate. Substrates with leaving groups on primary carbons use SN2. Substrates with leaving groups on secondary carbons can use SN1 or SN2, and substrates with leaving groups on tertiary carbons use exclusively SN1. These guidelines will work for most molecules you'll come across in organic chemistry, but there are important exceptions. For one, this neopentyl primary substrate won't do an SN2 mechanism very smoothly. Our leaving group is one carbon away from a sterically hindered tertiary carbon, so backside attack is really tough and the reaction is too slow to be practical. We also have substrates like PERC, chloroethene, or chlorobenzene, where the leaving group is directly attached to a double bond. Substitution by SN1 or SN2 doesn't happen at all. The sp2 geometry is all wrong for SN2 backside attack, and SN1 is pretty unfavorable too, because the vinyl or phenyl carbocations that would have to form are high energy. And then we have substrates with allylic and benzylic leaving groups, a leaving group that's one sp3 carbon atom away from a double bond. They use both SN1 and SN2 reaction mechanisms. Looking at one of these compounds, we might say, oh, there's a leaving group on a primary carbon, so it's gotta be an SN2 mechanism. But depending on reaction conditions, like if there's an excellent leaving group, a carbocation can form because it's resonance stabilized. That's the first step of an SN1 mechanism. This resonance stabilization of an intermediate cation is what makes allylic and benzylic substrates special. It also makes things even more complicated for allylic substrates. If a reaction proceeds by an SN1 mechanism, the two resonance forms of the carbocation intermediate can lead to a mixture of constitutional isomers as products. On the other hand, benzylic substrates only give one substitution product because they don't react on the benzene ring. After the structure of the substrate, the second key to picking a path is the role of the nucleophile. The nucleophile in an SN2 reaction is an active participant in the rate determining step. In our merry-go-round analogy, they were the playground bully who pushed someone off rather than waiting for them to leave. Nucleophilicity is a term to describe just how pushy the nucleophile's behavior is. Atom size plays a key role in nucleophile strength. The more polarizable the atom, the easier it is to get those electrons to attack and make a new bond. So nucleophilicity increases moving down a group on the periodic table. Halogens, which we talked about as good leaving groups, are also good nucleophiles. And really strong nucleophiles are often charged. So thiolates, hydroxide, and alkoxides are all examples of strong bullies or nucleophiles that use SN2 mechanisms. However, compounds like methanol, acetic acid, water, and other alcohols are relatively weak nucleophiles. Even with lone pairs on an oxygen atom, these molecules are uncharged and are less nucleophilic than their deprotonated cousins. They patiently wait to hop on the merry-go-round and are more likely to promote an SN1 reaction. And chunky sulfonates, which are good leaving groups, are very poor nucleophiles. Their electrons are tied up in resonance, not available to attack and make new bonds to a substrate. Our third and final key to help us decide between an SN1 and SN2 mechanism is the solvent. Solvents are usually liquids that are able to dissolve other things, like how perk dissolves clothing grime in dry cleaning and water dissolves table salt. There are two classes of solvents we need to consider in substitution reactions: polar protic and polar aprotic. Polar protic solvents, like water and ethanol, both have a proton on an electronegative atom. This type of polar bond with a proton lets them hydrogen bond to both cations and anions. This is good for SN1 mechanisms because the rate determining step is the substrate breaking up into ions. So polar protic solvents favor the SN1 mechanism. On the other hand, in an SN2 reaction, we need the nucleophile to be really available to push out the leaving group in the rate determining step. If our nucleophile is tied up by the solvent, it loses its pushing power and becomes weaker. So a polar aprotic solvent, which has no available hydrogens, can't hydrogen bond to our nucleophile, and an SN2 reaction is favored. Polar aprotic solvents have atoms like oxygen or nitrogen with a partial negative charge, and a polar bond, just not to a hydrogen atom. The polar bonds help these solvents dissolve organic compounds and the ionic nucleophiles often used in SN2 reactions. Some examples of polar aprotic solvents are acetone, dimethylformamide, and dimethyl sulfoxide, or DMSO. I'm gonna be honest, evaluating these key reaction conditions can feel complicated, but here's a trick we can use. Weak nucleophiles are often polar protic solvents and favor SN1. Since they're protic, the reaction is carried out under acidic conditions or generates a molecule of acid as a byproduct. So when we see acid as a reactant or product, think SN1. And on the flip side, reactions that take place under neutral or basic conditions tend to favor SN2. We can summarize all we've learned by adding different types of nucleophiles to the table we started in episode 20. Like I've mentioned over and over again, the best way to learn reaction mechanisms in organic chemistry is to practice, so let's do some rapid fire problems. We're going to put 4 substitution problems on screen and predict the likely mechanism and the products. Then we'll work through the answers, so pause right after the question if you want to solve them yourself. Ready? Here's the first problem, a reaction between a tosylate and sodium benzene thiolate, carried out in the solvent DMF. We have a secondary substrate with an excellent leaving group, so there's no definitive answer there. Our nucleophile is the real deciding factor. We have sulfur with a negative charge on a large atom, so it's a strong nucleophile, a playground bully. This reaction is SN2, which gives us the inversion of stereochemistry in our product. Here's the second problem, a reaction between an alcohol and hydrochloric acid. First of all, hydroxide is a poor leaving group, but remember, HCl is a strong acid that dissociates into H+ and Cl-, so there are protons floating around that can protonate the alcohol and make it an excellent leaving group, water. We have two keys here, a good leaving group and a tertiary substrate that blocks backside attacks. We get an SN1 reaction. This is reinforced by our little trick. There's acid in the reaction, so think SN1. The products are a mixture of the same and inverted stereochemistry at the reacting chiral carbon. For our third problem, how about this iodide reacting with acetic acid? Let's assume acetic acid is also our solvent here. We have a secondary substrate, a benzene ring with the leaving group separated from it by one sp3 carbon. So actually, this is a benzylic substrate that can make a resonance-stabilized secondary carbocation. That means it could do SN1 or SN2, and we have to look at another factor to make the final call. Acetic acid is our weak nucleophile and our polar protic solvent, and we clearly have acidic conditions. All signs point to SN1. Finally, our last problem, a reaction between a bromide and an acetylide anion. Our substrate here is a primary alkyl bromide, which rules out SN1 right away because SN1 reactions can only happen with secondary or tertiary substrates. To double check, our nucleophile is the strongly basic acetylide anion, and our solvent is polar aprotic. That ticks all of the boxes for an SN2 reaction. That's all we have for now, but keep practicing. Nucleophilic substitution reactions are some of the most common reactions in organic chemistry, so we'll see them again and again. In this episode, we learned that the main determining factor of SN1 or SN2 mechanism is the structure of the substrate. Weaker nucleophiles favor SN1, while stronger nucleophiles favor SN2. Polar protic solvents favor SN1, while polar aprotic solvents favor SN2. And acidic conditions characterize SN1 mechanisms, while neutral or basic conditions are typical of SN2. In the next episode, we'll add to our table even more as we learn about elimination reactions, where groups are lost from the substrate. Until then, thanks for watching this episode of Crash Course Organic Chemistry. If you want to help keep all Crash Course free for everybody forever, you can join our community on Patreon.